Hey everyone, welcome back. In today's video, we are going to tackle some key questions on linear algebra. We will cover important topics like linear transformations, rank, nullity, and the dimension of subspaces. If you find this video helpful, don't forget to give it a thumbs up, subscribe to the channel, and share it with others who might benefit. Alright, let's dive in. So let's see question 8. So what it is saying, for a positive integer n, let Pn denote the vector space of polynomials in one variable x with real coefficient and with degree less than equal to n. Consider consider the map T P2 to P4 defined by this. Then we need to basically check it is a linear transformation or not, and then they are asking about the rank and nullity, right? So if you have seen my videos on vector spaces, I already told you that vector spaces are not confined to just normal traditional vectors. uh, Vector spaces could be of anything. It could be of matrices, we call it matrix space. It could be of functions, we call it function space. In this question it is of polynomials. Okay, so for example they are saying that Pn denote is saying that Pn denote a vector space of polynomials in one variable. So there is only one variable x, and it is also it has also real coefficient and degree less than equal to n. So for example, if we have P2, so what is P2? P2 is nothing but, let us suppose, 1 plus uh, 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 2x plus 3x square. Let us suppose this is P2. All right. So uh, first tell me what is the dimension of P2. So the dimension of P2 is 3. Why? Because we have three coefficients, right? We have three coefficients, 1, 2, and 3. So we know that for an n degree polynomial, there are n plus 1 term possible, right? Because 1 is nothing but 1 times x to the power 0. 2x plus 3x square. Okay, so for this P2, the dimension of P2 is 3. Okay, so similarly the dimension of Pn is n plus 1. So basically for any n degree polynomial the dimension is n plus 1, because there are n plus 1, maximum n plus 1 terms possible. So I think it is clear that what is Pn. So it is saying that Pn denotes this Pn is the vector space of polynomials. So it contains all the vectors uh, which has one variable x as one variable x with real coefficient. Okay, and degree less than equal to n. So Pn contains polynomial like p1, p2, p3, p10, p100, p like anything, but you just need to define n. Now they have given us a transformation T. Now this transformation is from P2 to P4. Okay, this transformation is from P2 to P4. So you can say that it is transforming polynomials of type of this type, 8 of this type, a plus px plus cx square. Okay, T is transforming polynomials of this type from this to uh, uh, this becomes, and this won't be a, by the way, this will be, let us suppose, a1 plus b1x plus c1x square plus dx cube, a b c d e to the power x4. Yeah, so T is doing this transformation. Okay, so let us suppose M is the matrix representation of the transformation T. All right. If M is the matrix representation, then M belongs to 5. M is a 5 cross 3 matrix. Why? Because see, we are taking the vectors are coming. The vectors are input vectors are coming from P2, and the output vectors are going to P4. And we know that the dimension of P2 is 3 and the dimension of P4 is 5. So if the dimension of P2, that is the input vector space, is 3, then all the vectors should be of 3 dimension, should be 3 dimensional, right? That is this. And if the output space dimension is 5, that is the dimension of P4, then all the output vectors should be 5 dimensional. All right, so that's how I get the we got a matrix M dimension, that is 5 cross 3. So uh, so let us suppose we will construct a 5 by 3 matrix representation for this transformation. Before that, we are also given this mapping. This is the map. T is defined as T times P of X equal to uh, P of X square. So if this notation is you are getting confused, so we know that T is a transformation. It transform a vector V, which is lying in the input vector space, to a vector W, which is lying in the output vector space, right? So this vector is uh, in the input vector space. This vector is in output vector space. All right. So if basically here px is in the input vector space and px square is in the output, right? So let us suppose we need to transform what is uh, what is t of x. So it is nothing but x square, right? What is t of x square? It is nothing but x to the power 4. Similarly, what is t of 1? It is nothing but simply 1, because 1 square is 1. All right. Now this is nothing but a 5 cross 3 matrix. Okay. So we are moving from P2 to P4, right? P2 is of this type, P2 is of this type. So we need to check for the basis set for the input vector space P2. So what is the basis set? So any polynomial in the input vector space can be written as any polynomial a plus bx plus cx square in the input space is nothing but a linear combination of basically three basis element, which is 1 x and x square, right? Is a linear combination of this. So this set is nothing but the basis set. This is the basis set for P2. Why? Because you take any polynomial in the input vector space P2, take any polynomial. If that polynomial is nothing but a linear combination of these three elements. Okay. And similarly, what is the basis set for the output vector space? We know that this is the output vector space A1, B1, this one. So uh, any polynomial in the in P4, any polynomial in P4 is nothing but a linear combination of 1 x, x square, x cube, and x4, right? So this is the basis set. This is the basis set, basis set for P4. All right, this is the basis set for P4. Now we know that a matrix representation of a linear transform is nothing but where the basis elements lies, right? So for example, if I say that this is a matrix 2 3 0 1 5 1 and 7 0 8. Okay, so what this basically means is where I had landed. This is where I had landed, right? Similarly, this is for j hat and this is for k hat, where k hat landed, right? So what are I hat, j hat, k hat? These are nothing but the basis vectors for the input vector space R cube, right? So similarly, the column vectors of this 5 cross 3 matrix is nothing but where these basis or these basis element of the input vector space lies. We are moving from P2 to P4. We are moving from P2 to P4. So the first column vector, the second column vector, and the third column vector is nothing but where this 1 x and x square landed after applying the transformation T. Okay, so we need to simply check T of 1, T of x, T of x square, right? Because what is this? This is nothing but T of k hat, right? This is T of k hat. This is T of j hat. This is T of I hat, right? This is T of I hat. So uh, we need to check where 1x and x square landed. We already checked that, right? T of 1 is 1, T of x is x square, T of x4 is x4, right? So we can say basically that T of 1, which is 1, this can be written as 1 plus 0 time x plus 0 time x square plus 0 time x cube plus 0 time x to the power 4, right? So this T of 1 is nothing but the vector 1 0 0 0 0. Okay, so you can simply say this column vector represent T of 1, this represent T of x, and this represent T of x square. All right, and this is the 1x x square x cube and x4. That is the output vector space. So T of 1 landed at 1 0 0 0 0. Similarly, T of x is x square, T of x is x square. This can be written as 0 plus 0 time x plus x square plus 0 time x cube plus 0 time x4. Okay, so this is nothing but 0 0 1 0 0. So rank of this matrix, rank of the transformation T is same as the rank of the matrix, right? And the rank of this particular matrix is nothing but 3, because we have three linearly independent columns. So these are the three linearly independent columns. All right, we know from fundamental theorem of linear algebra is that the dimension of column space, the dimension of the column space of a matrix, the dimension of the column space plus dimension of the null space of the matrix M is nothing but dimension of the input space Rn, which is n, right, for an M cross n matrix. So dimension of column space is nothing but the rank. So rank of M plus this is the nullity of M, and this is basically n. In our case n is 3. In our case n is 3. So we can simply say that rank of m is 0, because sorry, nullity of m is 0 because rank is 3. So if nullity of m is 0, then the nullity of the transformation T is also 0. So it is same. All right. So we get rank as 3, nullity as 0. And also this is a linear transformation. So if you want to find what is a linear transformation, I have given explained in this video of linear transformation. So if you want to find any transformation, check any transformation is linear transformation or not, you need to check for this condition, that transformation of CV plus DW should be this. Then option B is correct. Let's see question number 9. We have seen in our lectures that for example you have this 3 by 3 matrix, okay, and it is a symmetric matrix. So if it is a symmetric matrix, then for example you have ABC, then this is B, D, E, then this is D, this is E, then this is F. So basically you have here, you have in a 3 cross 3 matrix, here you have 1 2 3 4 5 6. These 6 values are unique, right? The remaining 3 are the same values. Okay, so for any matrix, this element, these two elements and these three elements will be the one uh, which is unique, right? So for example, this the number of unique elements here is 1 plus 2 plus 3. Okay, but this can be generalized for higher degree matrices, right? So we can say that the number of unique element in a n cross n symmetric matrix is nothing but 1 plus 2 plus 3 up to so and so forth plus n. Okay, so this is nothing but number of unique elements in a n cross n matrix, right? N cross n symmetric matrix, right? And this sum is nothing but n plus 1 by 2. And we have seen that this is the number of unique elements in a symmetric matrix is actually the dimension of that symmetric matrix. So we can say that dimension of a symmetric matrix of n cross n is nothing but n plus 1 by 2. right? And in case of 5 cross 5 matrix, this is nothing but n is 5. So we can say that this is 5 plus 1 by 2, that is 15. So we can say that dimension of a symmetric 5 cross 5 symmetric matrix is 15. But there is one more thing. We are given that the symmetric matrix with trace 0. So this is like you have added one extra condition, right? So this is 15 is the dimension of 5 cross 5 symmetric matrix. But we are interested in 5 cross 5 symmetric matrix with trace 0. And I have already told you that if you want to find the dimension of a subspace, then you need to whatever the original dimension is, let us suppose the original dimension is a, then not a, let us suppose the original dimension is alpha, then you need to subtract the number of linearly independent restrictions. Okay, restrictions. And in this case we have only one restriction. It is saying that the trace is 0. So if you see this example, this is saying that a plus d plus f should be 0, because the trace of a matrix is nothing but the sum of its main diagonal elements. Okay, so in our case the number of linearly independent restriction is only one. So for us the dimension of the given subspace W, this is the given space W, is nothing but the original dimension, which is 15, minus number of linearly independent restriction, which is 1, that is 14. So dimension of this subspace W is nothing but 14. Now see the next question, LA10. So this question is very similar to the question which we have seen earlier, that is our first question. So it is similar. So I would highly recommend to you to pause the video and solve this question by your own. We are given a transformation V to V. Okay, be the map and the transformation is given such that T P times X is P dash 1. Okay, so in this question we were given the map P2 to P4. Okay, uh, but here we are given a generalized map. Okay, then it is asking which of the following are correct. So basically it is asking about kernel and range, and I have already told you that kernel is nothing but nullity. It is nullity. Okay, so for example, so to solve such question, we can take a transformation like P2. Let us suppose we take a transformation from P2 to P2. Okay, we will solve for one case and then we will generalize it for any Pn. Okay, because the options are given in terms of n, right? So this is P2 to P2. Now what is P? P is a polynomial with degree less than equal to n. So we can say P is a plus bx plus cx square up to, this is Pn, up to uh, some variable alpha times x to the power n. Okay, so what is P2? P2 is a plus bx plus cx square. Now we need to find the rank and nullity of this transformation. A is the matrix for transformation T. Okay, A is the matrix for transformation T. So we need to find the rank and nullity of A. That would be same as the rank and nullity of T. So I have already told you that because this is P2 to P2, right? This is P2 to P2. So here n is 2. We have taken n is 2. So what will be the dimension of matrix? The dimension of matrix is not 2 by 2. It will be 3 by 3. Why? Because a 2-degree polynomial has three terms, right? That is x to the power 0, x to the power 1, and x to the power 2, right? So the first column vector is nothing where the first basis vector land, the second is the where the second basis vector land, and the third column vector is where the third basis vector landed, right? So we know that for P2 the basis set for P2 we have already seen in the previous question. The basis set for P2, it is uh, this basis set for P2 is 1x and x square, because any polynomial of degree 2 is nothing but a linear combination of these three terms, right? Any polynomial of degree 2 is nothing but a linear combination of 1x and x square, because a times x plus b times x plus c times x square is nothing but a linear combination of 1x and x square, right? So the column vectors is nothing but where the transformation T take the first basis vector 1, where the transformation T took the second basis vector x, and where the third transformation, where the transformation T maps the third basis vector Tx square, right? So we need to calculate this. So we need to find T times P of 1, because T is given as this, T times P of x equals to P dash 1. So this is P dash 1, right? So in our case, the derivative of a constant is 0, right? And so this is simple. Now we will take the second basis vector t times p of x, right? So this is the derivative of x is nothing but 1, right? Then we will take t times p of x square, right? So derivative of x square is nothing but 2x, and then we are given that t times p of x is whatever derivative you get, to that derivative you need to basically put 1 for the values of x. So for the basis vector 1 and x, we were already getting constant. For 1 the derivative is 0, so there is no point of putting 1, because there is no x terms here. Same goes for the second basis vector x, but for the third basis vector x square, there is an x term, so we need to put 1 for x, right? Because it is given that t of p of x is nothing but the first derivative of p at 1. This is first derivative of p at 1. So let me write it. This is uh, first derivative of p at x equal to 1. All right. So this will be 2 times 1, that is 2. Now this is nothing but yeah, also we can write this 0. Basically this is how we get this 0 using these basis vector. That is basically all needs to be 0, right? All needs to be 0. 0 times 1 plus 0 times x plus 0 times x square. Similarly we can get 1. 1 is nothing but 1 0 0, and for 2 we can get this 2 0 0. Okay, after doing the first derivative, you need to put the value of x equal to 1. So no matter which basis vector you transform, because you need to put some value for the variable x, you will always get some constant 0 1. So here you get 2x, right? Here you get 2x. If the transformation is not p dash 1, if it is not this, if it is simply p dash of x, then you will get 2 times x. Then this won't be 2 0 0, it will be 0 2 0, right? But because they are saying that after taking the first derivative we need to put x equal to 1, so no matter what basis vector you transform, you will always get a constant, right? So that's why the resulting matrix is this. And now if you check this matrix, there is only one independent column. This is the only independent column vector, right? This is the only independent column vector. So so no matter what is n, no matter what is n, even if n is 3 4 5 6, no matter what is n, you will always get this type of matrix where you will only have one independent column vector. Why? Because after transforming you are always getting a constant. If you are always getting a constant, then all the rows, no matter what is n, if n is 5 7 10 whatever it is, all the rows except the first row will be 0. If only the first row is 0, if only the first row is non zero, then we can say that there is only one independent column vector, right? So the rank of transformation T is nothing but the rank of the matrix A, which is 1 this in this case. Okay, and if that is 1, then what is the kernel? What is the kernel of T? That is nullity of A. Kernel of T is nothing but the nullity of A. So in our case, this is P2 by 2. This is nothing but this is 2, right? Because we know that this is a 3 by 3 matrix, so it is nothing but n minus the rank, which is 1. So 3 minus 1 is 2. Okay, and what is 2? 2 is nothing but n. So we can say the nullity or the kernel of transformation T is n only. Okay, so this option, the option A and B are correct. That is, kernel is n, ranges. Okay. So that's all for this video. So if you like my video, then please subscribe my channel and share with others. Till then, bye. Thank you.